In this video, we're going to talk about what autocorrelation is, what its consequences are, how to detect it, and what to do if you find it. In the classical regression model, we assume that the error terms for different observations are independent. In the case of time series models, what that means is that the error term in one time period is independent of the error term in other time periods. And as a result, if we take the error terms in any two different time periods, their product should equal 0. So the question is, what happens when that assumption is violated? In earlier videos, we talked about positive and negative first-order autocorrelation. Positive first-order autocorrelation is characterized by clusters of positive error terms grouped together and clusters of negative error terms grouped together. Will never be quite as smooth and regular as the pattern depicted here, but we tend to observe this sort of clustering. Negative first-order autocorrelation, as in this diagram illustrating the error terms versus time, would tend to alternate in sign more often than not. So we'd see positive error terms being followed most often by negative error terms and vice versa. One thing we should note, though, is that we might appear to find autocorrelation when we've really just specified a model incorrectly. For example, if y and x are two variables that grow over time, and y is growing at a rate that's exponential with respect to x, a graph of the relationship would look something like this. If we estimate a linear relationship between y and x, when the appropriate relationship would be between the log of y and x, we'd observe a clustering of positive error terms, followed by a clustering of negative error terms, followed by a clustering of positive error terms. So in some cases, when you find apparent autocorrelation, it's really just a sign that you've specified an incorrect functional form. And that's something you may want to consider when you find cases of autocorrelation. Now, let's consider the issue of first-order autocorrelation in a bit more detail. We're starting with a multiple regression model where y can be written as a linear combination of k independent variables plus an error term. And the error term we're assuming when we have first-order autocorrelation can be written as the current period's error term is equal to rho times the error term in the prior time period plus what we call a white noise error process, epsilon t. The expected value of a white noise error process is 0, and the expected value of the product of any two epsilons is 0 when t is not equal to s, but the variance of epsilon t we define to be sigma squared sub epsilon. And this white noise process is ultimately the type of thing we've been assuming about the error terms in regressions under the classical regression model. So we're decomposing the error term into one part that's explained by the past and another part that's purely random. If we compute the expected value of ut times ut minus 1 when there's a first-order autoregressive process, we can write it as the expected value of ut times ut minus 1 as the expected value of ut, which equals rho ut minus 1 plus epsilon t times ut minus 1. Multiplying out that relationship in the square brackets, that's equal to the expected value of rho ut squared in period t minus 1 plus ut minus 1 times epsilon t. The first term simplifies to be simply rho times the variance of the errors because that variance is the same in all time periods. And the second term simplifies to be 0. And as a result, the expected value of the product of ut and ut minus 1 will be equal to rho times sigma squared, which is not equal to 0, which is why this violates the assumptions of the classical regression model. The consequences of first-order autocorrelation are that your OLS estimators remain unbiased and consistent, but they're not blue, they're not efficient. Essentially, there's some information in the error terms that you're not using when you construct estimates of the parameters. And it turns out we can get an efficiency improvement if we take into account the fact that there's autocorrelation in the error terms, that past error terms contain some information about future error terms. A more serious problem, though, is that the estimated variance in this case turns out to be biased. And as a result, our standard errors are biased, and usually it's a downward bias which results in biased estimates of your t-ratios, which is almost always going to be an upward bias. And what that means is that while you do have unbiased and consistent estimates of model parameters, you're not able to use the t-ratios that you derive from that regression to be able to test hypotheses appropriately. And because there's an upward bias in the t-ratios, what that means in practice is some things may appear to be significant when they would not be if we had corrected for the presence of autocorrelation. The simplest test for first-order autocorrelation is a Durbin-Watson statistic that appears on the screen. We compute that by, in the numerator, taking the difference between the error term in time period t and the error term in time period t-1 and squaring that, and we can do that for periods 2 to n. We lose the first one since we don't know what happens in the time period before time period 1, and we divide that by the sum of the squared error terms. With a little bit of algebra, you can show that the Durbin-Watson statistic will be approximately equal to 2 times 1 minus the estimated value of rho. If the value of rho is 0 and there's no autocorrelation, then the numerator term would be roughly 2 times the sum of the u hat t squares. If rho is positive, you're going to end up with a value of the Durbin-Watson statistic that's less than 2. If rho is negative, you're going to end up with a value of that statistic that's greater than 2. What happens when you use a Durbin-Watson statistic is if there is no autocorrelation, you'd end up somewhere close to 2. And the way we use a Durbin-Watson statistic is to test whether rho equals 0 versus the alternative hypothesis that rho is not 0. And if rho is equal to 0, the Durbin-Watson statistic should be approximately 2. Unfortunately, unlike all the other tests that we've talked about in this class, there is not a well-defined threshold value for the upper and the lower tail. What happens is that when you compute the Durbin-Watson statistic and you use a Durbin-Watson table, you will be given an upper and a lower bound for the Durbin-Watson statistic. If we have an apparent positive first-order autocorrelation, we're going to be looking at the values on the left side of that numbered line there. And we would always reject the null hypothesis if the Durbin-Watson statistic falls below the lower bound for that statistic. If it falls above the upper bound, you would not reject it at whatever significance level you're using. Unfortunately, there's an uncertainty region where if it falls in that region, it's not clear whether you should reject the null hypothesis. And the safest thing in general is probably just to treat the upper bound as if that's the effective lower bound and assume that there's autocorrelation whenever it falls below the upper bound, just to be safe, because the consequences of not addressing the autocorrelation can be relatively severe. In the upper tail, we get the same type of thing, except we take 4 minus the upper and lower bounds, and that determines the uncertainty region. If we fall below 4 minus the upper bound for the Durbin-Watson statistic, we don't reject the null hypothesis. We definitely reject it if it's above 4 minus the lower bound of the Durbin-Watson statistic. If it falls between 4 minus the upper and 4 minus the lower bounds for that, again, the safest practice is to assume that you have found autocorrelation. Now, let's talk about how to correct for this. If we know the value of rho, there's a relatively straightforward solution to this. So our basic equation is given by y as a linear combination of the x's, and we're assuming that ut is a first-order autoregressive process and equal to rho times ut minus 1 plus that white noise error process. If we lag that equation one period, we get this, where y in the period t minus 1 is just a linear function of all the x's and the error term in period t minus 1. Now, let's take this equation and multiply both sides of this lagged relationship by negative rho. We end up with negative rho times yt minus 1 equals negative rho times the whole right-hand side of that equation. Let's take the first equation at the top of the screen and subtract minus rho yt minus 1 from this. And what we end up with is this, where we have yt minus rho yt minus 1 is equal to a new constant plus the sum of each of the beta coefficients times xjt minus rho times xjt minus 1. The important thing to notice here is that very last term, which equals ut minus rho ut minus 1. If you think about that a little bit and we compare it to what we see at the top of the screen, we can observe that that last term is just equal to epsilon t. So by making this transformation, by lagging the equation and multiplying it by negative rho and subtracting that from the original equation, we've ended up with a new equation where the error term is just epsilon t. And epsilon t, remember, is uncorrelated across time. Essentially, what we've done is we've transformed this equation from one where we had first-order autocorrelation to one where we've removed the first-order autocorrelation by this process of lagging the relationship, multiplying by rho, and then subtracting that from the original value of each of the variables. We call this approach quasi-differencing. And you quasi-difference a variable by taking its current value and subtracting rho times its previous value. You quasi-difference the dependent variable and each of the independent variables, and then you run a regression of the quasi-differenced y against the quasi-differenced x variables. And this equation satisfies the condition of the classical regression model, and as such, you could estimate all the model parameters. One special case of this is that if rho happens to be equal to 1, then a unit root is said to exist, and then that quasi-differencing would be reduced to simply differencing, where you measure the change in y as a linear function of the changes in x's. But again, that's only if we have a value of rho equal to 1. This is an example of an approach in econometrics known as generalized least squares. And the basic strategy is that if one of the assumptions of the classical regression model is violated, you transform the model so that this transformed model satisfies these assumptions. And you estimate that transformed model, and that gives you estimates that are unbiased, consistent, and are blue, the best linear unbiased estimators. The problem, though, in practice is that we don't know the value of rho. There have been several techniques suggested to estimate a model when rho is unknown. One procedure, and the earliest one that was used extensively, was the CochranOrca procedure. And under that procedure, you estimate the model using ordinary least squares. You save the error terms. You regress the error terms on the lagged error terms without a constant to estimate a value of rho. Then you use that estimated rho to quasi-difference your dependent and each of the independent variables. And then when you estimate that, you now get estimates of beta 0 through beta k. Once you've done that, you would then be able to get new estimates of the error term, and then you'd keep repeating this until eventually the parameter estimates converge. This procedure will result in unbiased and consistent estimates of all model parameters and model standard errors. So your t-ratios from this would be perfectly valid for hypothesis testing. One of the problems with the CochranOrca procedure is that you lose one observation, which may not seem like much, but when you're only looking at the quasi-differencing, we lose quite a bit of sample information. The PriceWinston estimator is similar to the CochranOrca procedure, but it applies a different transformation to the first observation. This is discussed in more detail in the textbook, but basically it gives you back that first observation, and Monte Carlo studies show that by including that first observation, we end up with a substantial efficiency gain compared to the CochranOrca method.